Welcome back to this next video in which we are discussing the electrocardiogram or the ECG. Okay, so we started off with a review as to the order in which the electrical signal propagates through the different portions of the heart, and we talked specifically about this new concept of the cardiac vector, which is this direction in which current is flowing, the net direction in which intracellular current is flowing. Okay, so what we now want to do is use this understanding that we have concerning the cardiac vector at different portions of the cardiac cycle to understand the ECG. Okay, so when I was introducing the ECG, I told you about the fact that often the thing that's actually done clinically is what's known as a 12-lead ECG, and in fact a 12-lead ECG is in fact 12 different ECGs. We're going to start simple, and we're just going to try and understand one of these, one of the 12 leads of the 12-lead ECG. So one ECG. The others are all just modifications of it because they're slightly different angles. Okay, so if we understand one, we will have a very good basis for understanding all of the others as well. Okay, so let me tell you then what we're actually going to be measuring. So, we are going to stick electrodes onto our person, and initially we're just going to put 2 electrodes. When we go on to do the 12-lead ECG, we'll have to put loads more electrodes on as well. But initially we're just going to put on 2 electrodes. Okay, so we are going to have our person here, so I'll just draw a little stick man, and what we're going to do is we're going to put 1 electrode on the right arm here, so this is his face here, he's smiling at us, so this is his right arm here. And we're going to put 1 electrode on his left leg, like so. So we're going to do the exact 2 that I talked about here. And what we're now going to do, this is the basic principle, we are going to measure the electrical potential difference between those 2. And the idea is that because of the electrical activity in the heart, because of these currents that are moving around inside cells within the heart, we're actually going to notice changes in the electrical potential at these 2 points, and we will see that by measuring the electrical potential difference between the 2. Okay, so what we're going to measure then is the electrical potential difference between the 2, and we're going to go from the right arm to the left leg. So we're going to ask, if you were to move from the right arm to the left leg, how much does the electrical potential at that point change? So if I was to go from here to here, how much would the electrical potential go up or down? So remember, electrical potential is this value that's ascribed to every point in 3-dimensional space. The right arm where the electrode is will have a certain electrical potential, the left leg will have a certain electrical potential. We're now asking what's the difference between those 2. Specifically, we're asking what would I have to add on to the electrical potential at the right atrium to get to the electrical potential at the left leg. And that's what we are going to be following with an ECG. We're going to follow this value over time, and it is going to alter because of the electrical activity within the heart. It's going to alter on a rhythmic basis with the cardiac cycle. Okay, so the next thing I want to explain is ECG paper. Okay, what are the units for ECG paper? So this graph is going to be drawn on special paper known as ECG paper, and of course we're going to have time along the x-axis, and we're going to have electrical potential difference in millivolts along the y-axis. However, I need to explain to you the type of paper it's going to be drawn on. So it's going to be drawn on paper with loads of tiny little boxes, and the little boxes will be 1 millimeter by 1 millimeter, so they'll be this sort of size here. So 1 millimeter square paper. Now, every 5 millimeters you have larger boxes as well. So let me draw now one of these larger boxes. So not only will you have the tiny boxes, so the paper will be split into loads of these tiny boxes, but also you'll have larger boxes which will have 5 times 5 millimeter square boxes in, so like so. So I'm trying to draw. There we go, so you've got 25 of the little 1 millimeter squared boxes in this larger box. Okay, so that's how ECG paper is divided up. It's divided up into 1 millimeter squared boxes, and then you have these larger boxes which are 5 millimeter by 5mm boxes. Okay, right, so that's firstly the paper, and we call this paper ECG paper. Now, as I say, on this paper we will have the x-axis representing time. So we'll have time along the x-axis like so, and every 1mm will represent a certain amount of time. Specifically, it will represent 0.04 seconds. So there is 0.04 seconds per 1mm. Okay, so every 1mm along in the horizontal direction, we will be going forward 0.04 seconds. So how many seconds will we be going forward in a big box, a 5mm by 5mm box? Well, we'll just have to multiply this by 5, so we'll be going along 0.2 seconds. So that means that overall 5 big boxes, okay, 5 of these boxes in red, so it will go on to maybe about there, okay, would be 1 second. Okay, so there's an understanding of the units then. Now let's do the units in the vertical. So we'll also have millimeter divisions up in the vertical, and of course vertical is going to represent our voltage. So here will obviously be a voltage of 0, but when we go up 1mm, how much will the voltage change? Well, that will change by 0.1 millivolts. Okay, so 0.1 millivolts rather, per 1mm. So every millimeter vertically represents 0.1 millivolts change in the electrical potential difference across the cell membrane. Sorry, not across the cell membrane, between these 2 points. Okay, so those are the units then, those are the scales rather. Okay, so every 1mm vertically represents 0.1 millivolts in electrical potential difference across the 2 electrodes, and 1mm horizontally represents 0.04 seconds. Okay, so we can now plot a graph on here of what the electrical potential difference between the electrode on the right arm and the electrode on the left leg is going to do over time. And what we will get is an ECG pattern. Right, so that's all of the basic setup. What I now want to actually do is show you what the ECG pattern looks like. So I think the best way to actually do this is for me just to firstly write down what you actually get, draw down what the ECG pattern actually looks like so that we've got it on paper, and then I will try to justify why each of the bits occurs, okay, rather than trying to talk you through as I draw it out what's going to occur. I think the best way to do it is just to chuck it all down on paper. Okay, so I'm not going to attempt to actually make myself a 1mm by 1mm square grid. Instead, I'm just going to draw out what the ECG pattern will look like. Okay, so the first portion of the ECG patterns, if we start off here, and we'll say that we are lucky enough to start our ECG when the sinoatrial node starts to send out an electrical impulse to the atria. Okay, so what you then start off with is a little wave that looks like so. Okay, and this is called the P wave. And I will exactly justify why you get this, but for now I'm just going to draw it. So here, this is the P wave, and actually as we go through it, I'll tell you the time sort of scale that we're talking about here. So this sort of P wave here, which is a deflection upwards, so you're getting a positive electrical potential difference between the right arm and the left leg here. This will generally last for about 0.08 seconds. Okay, so that's the time interval here. I will not tell you what the actual deviation in electrical potential difference is here, because that will depend on so many different factors. So for instance, where you actually put the electrodes exactly on the leg, how big the person is, all of those sort of things. So I'm not going to actually be able to give you a value for what this deviation would be. Okay, but I will give you time values. So the P wave would last for 0.08 seconds, then we'd have another flat bit where the electrical potential difference between these 2 points goes back to being 0 here, and that would last for another 0.08 seconds. So we're going to be working on the assumption that the overall cycle duration for each cardiac cycle is 0.8 seconds. So all the portions of this entire ECG that I'm drawing out here must add up to 0.8 seconds. So each of these bits that I've drawn so far are taking up a tenth of that time. So here's the P wave, and I think I'll just add a bit of colour onto here. So we have the P wave in orange, and then we've got this flat portion. And this entire portion that I've now drawn, the P wave plus this flat portion that follows it, this has a name. This is known as the PR interval. Okay? So that's all called the PR interval. So the P wave along with the flat portion that follows it, which overall takes 0.16 seconds, that's called the PR interval. Now what we're going to get is we're going to get something called the QRS complex, and this, as we'll see, is what you get once the this electrical signal has actually started propagating along the ventricles. Okay, so you'll firstly get a little wave downwards, which is called the Q wave. You'll then get a big wave upwards, which is called the Q wave, the R wave, and then you'll get another wave downwards, which is called the S wave. Okay, so I'll label all of these up. So this little deflection downwards here, this is known as the Q wave. This big deflection upwards, this is called the R wave. This deflection downwards is called the S wave. And this entire period here, which I will colour in green here, like so, this spiky portion, very recognisable when you see a real ECG. This is known as the QRS complex, and you might be able to guess in my simple splitting the cycle duration up into nice simple numbers how long this is going to take. This takes approximately 0.8 seconds. Okay, so of course these are only rough guides, these times here. I have picked numbers that are roughly correct to make it all work beautifully so that the numbers are nice and they're all a tenth of the entire cycle duration here. Okay, but these are only rough estimates. So the QRS complex is usually in duration around 0.08 seconds, however. But don't take them as, God-given numbers here. Okay, so there we have the QRS complex, and as I say, this is the portion that represents the electrical activity, the depolarization of the ventricles. Okay, and we'll understand why this is, and you might like to start thinking potentially why. Okay, look, we've got one downward deflection, then upward deflection, and one downward deflection again. What did we previously see about the cardiac vectors for ventricular depolarization? Well, firstly we had septal depolarization, and that went in one direction. Then we had major ventricular depolarization. I'll just bring this picture down. So there's septal depolarization going up in that direction. Then we have major ventricular depolarization going in this direction, and then we had the posterior portion depolarization, which went in that direction. So it's a similar pattern, and indeed it's exactly the same pattern. So we'll come back to that. Then what we'll have is another flat portion here, okay, which is known as the ST interval. So this is where there is no noticeable electrical potential difference between the right arm and left leg. So I'll colour in the ST interval in yellow here. Oh, and by the way, the reason the PR interval here is called the PR interval is that it's the time from the P wave to the beginning of the QRS complex. So the R is for the R wave in the middle of the QRS complex. And can I just actually change this? I think it's more commonly called the ST segment than the ST interval. I'm not sure that really matters, but usually people refer to that as the ST segment. I think if you called it the ST interval, everyone would know what you meant, but I think the utterly correct name for that is actually the ST segment. Okay, and this is so called because it's going to be between the S wave here and another wave which will be called the T wave. And again, the ST segment will last for approximately 0.8 seconds here. So again, another tenth of our entire cycle duration there. And then what we're going to have is another wave, which is going to be an upward deflection wave called the T wave, and this is going to be a very long one. This is going to last for approximately 0.16 seconds. So I'll have this in purple here, and we'll see that this actually represents ventricular repolarization. Okay, and we've talked about how that has a cardiac vector as well. So this is the T wave here, like so, and then after that, the ECG just remains flat until the next cardiac cycle begins. So after this, it's just going to be flat, and then of course it's going to be flat for the rest of the time. So how much time have we got left over here? Well, we've got 0.8 seconds, 1, 2, 3, 4, 5, 6 times, so we now need 4 more 0.8 seconds to take us up totally to 0.8 seconds, and of course that will be 0.32 seconds. So this is a bit out of scale because I haven't got enough paper here. It would really go off the side here. Okay, and that's the final portion. Before then you'd have another P wave after that. Okay, so that's then what this ECG pattern will actually look like. If we drew this graph, if we let this device run and it was to actually draw us an ECG trace between the right arm and the left leg, this is what it would look like. This is how the electrical potential difference from the right arm to the left leg is actually going to vary over a cardiac cycle. And our job now is to understand why it varies like this. Okay, so let's begin with the P wave here. So this represents atrial depolarization. So let's go back up to our picture of the heart here. So depolarization is set off from the sinoatrial node here, and it's going to spread down all of the cardiomyocytes here. Okay, and of course what we've discussed is that as the electrical signal propagates down the cardiomyocytes, what is actually happening is you're getting positive current moving from one cardiomyocyte to the next in the same direction as the direction of propagation. So overall you have an intracellular current in this direction of the cardiac vector. Now that is a real current. You are moving positive charge in that direction. When you move positive charge, that changes the electrical potential at areas. We are measuring electrical potential up at the right atrium and, up at the, I can't say look at RA and not think right atrium. The right arm, I apologise. So we are measuring electrical potential difference between these 2 points. Now, if we are moving charge in this direction, we're moving positive charge away from the right arm up here. Okay, so the electrical potential there will go down when we do this because we're moving positive charge away from it. Positive charge near an area makes the electrical potential at that area higher. So moving positive charge away from the right arm will lower the electrical potential there. Okay, meanwhile we're moving positive charge towards the left leg, down towards the left leg. Okay, so electrical potential there will go up because we're moving positive charge towards it, and having positive charge in an area boosts the electrical potential there. So if we now ask about what is the electrical potential difference from here to here, well, if this one's going down and this one's going up, the amount that you would have to step up when you moved from here to here is going to become positive. Previously they had the same electrical potential, now this one's gone down, this one's gone up, so now we're going to have a positive electrical potential difference between them. That's why you initially get this going up here. Now that explains why it goes up. Why then does it go down? Okay, well remember, electrical potential differences are not stable. Charged particles are forced to move by electrical potential differences. Okay, so what will very quickly happen, once you've transiently established this electrical potential difference between these 2 points, what will happen is a current will move in the opposite direction. Okay, we have got this intracellular current inside the cardiomyocytes moving as the depolarization wave spreads down the right atrium. What will now happen is the exact reverse. Current outside the cells will move in the opposite direction to balance it. Okay, but there will be a delay between that happening. You'll establish electrical potential differences all over the body by moving this current in this way, and as I say, electrical potential differences are not stable. They make charged particles move, and the charged particles will move in a direction to try and reverse the electrical potential difference. So what will now happen is positive charge will move all over the place back in the opposite direction to destroy this electrical potential difference, and that then is why it goes down. So you're going to have extracellular currents which are going to move because of course the entire body is in electrical equilibrium. Charged particles are free to move around, ions can move all over the place. As soon as you establish this electrical potential difference transiently, it's not going to last long because it's going to force charged particles to move, and they'll move it will force them to move in a direction which will lead to the destruction of the electrical potential difference. So what will then happen is it will come back down. Okay, now what's this black portion, the PR interval here? Well, this represents the portion where the depolarization, the electrical signal, is propagating through the AV node and the ventricular conduction system. So it's when it's propagating through the AV node, the bundle of His, the right and left bundle branches, and the Purkinje fibers. That's what the PR interval represents. Okay, when the electrical signal, the action potential, is just propagating through those small conduction systems. And you might ask, but surely, there's a current going between the cardiomyocytes in those conduction systems. Surely they have a cardiac vector, and surely that would lead to an electrical disturbance. These conduction systems are very, very small. Okay, so yes, although there will be currents moving down them, they're far too small to actually see. The reason we saw this previously was you had a huge number of atrial cardiomyocytes which were all partaking in this current, okay, and that was all summing together to give you an actual noticeable effect. The conduction pathways are too small to actually give you a noticeable effect, and that's why the electrical potential difference between the 2 points now remains 0. The electrical potential at the 2 points remains equal. Okay, now what's going to happen is the electrical potential difference is actually going to be unleashed on ventricular cardiomyocytes. And where does it get released first? Well, we know that the left bundle branch releases it onto the septal myocardium, and then it will propagate up the septal myocardium in this direction, in the opposite direction to how the wave of depolarization propagated in the atria. So now what you're going to get is you're going to get positive current going in the opposite direction, and that therefore leads to a deflection downwards rather than upwards, because you're now moving positive charge towards the right arm up here and away from the left leg. So you're going to boost the electrical potential up at the right arm, and you're going to lower it down by the left leg. So now what you're going to get is a deflection downwards, and that is the explanation that we have for the Q wave there. So the Q wave is septal depolarization. It's the propagation of the depolarization up the interventricular septum. Okay, now you can then obviously see the reversal of this a little bit, but really what this huge upward slant here is now major ventricular depolarization. Okay, so the R wave next. So what's now going to happen is the ventricular conduction system is going to unleash the action potential onto the major portions of the ventricular muscle, all of this portion, the huge portions of the ventricular walls. And we know that it's released onto the inner myocardium, the subendocardial myocardium, and propagates out towards the subepicardial myocardium, the outer myocardium. And overall, the direction of current flow, the cardiac vector, is again downwards. So we're now going to get a massive deflection upwards, just like in the P wave, and this is what the R wave is here. So part of this upward portion here will be the reversal of the Q wave, but mainly it's dominated by the R wave upstroke here, as the current is moving down in the direction towards the left leg there, and we're getting this rise in the electrical potential down at the left leg and drop in the electrical potential up at the right arm, and that's what's causing this sudden electrical potential difference between the 2 points. Now what's going to happen, of course, is it's going to reverse. It's going to drop back down for the same reasons we've talked about before. Okay, so once you've established this large electrical potential difference between the right arm and the left leg, that's not stable. Extracellular currents will now move to get rid of that, and that's why we come down here. And then finally we drop back down below this 0 electrical potential difference line. And by the way, the line of 0 electrical potential difference, this is known as the isoelectric line. So just a piece of terminology that you'll often hear people talk about. So the isoelectric line just means the same electrical potential is at 2 points. So iso means same, electric obviously refers to electrical. So this is the line where the 2 points that you have the electrodes have the same electrical potential. There is no electrical potential difference between the two. Now we've got the S wave, and the S wave, of course, is where the conduction system has finally unleashed the action potential onto the posterior portions of the ventricular muscle here, and now it's propagating backwards in this way along the posterior walls of the ventricle, and of course the cardiac vector in that case is pointing this direction again. Okay, so you're getting positive charge moving overall towards the right atrium, the right arm. Right arm here, I should write it out in full, in fact I think I will. This is the right arm, okay, up towards the right arm and away from the left leg. And therefore you're going to get the electrical potential rising up at the right arm and lowering down at the left leg, and therefore you're going to get a negative electrical potential difference between the two, because when you move from here to here, you actually have to go down electrical potential. Okay, and then of course the S wave, it's reversed by extracellular currents moving to destroy it. Okay, so then we get back to the isoelectric line, and here we are at the ST segment here, which lasts for about 0.08 seconds. So what does the ST segment represent? Well, this represents where all of the ventricular cardiomyocytes are currently undergoing action potentials, but they're all currently in the plateau phase of their action potentials. So they might all be contracting. So if you know the excitation contraction mechanism, calcium will be coming in because of the electrical signal, the action potential, having opened the L-type voltage-gated calcium channels, and you'll be getting release of calcium from the sarcoplasmic reticulum by the type 2 ryanodine receptors, and that will then cause the cardiomyocytes to contract. Okay, then what's going to happen is repolarization will begin, and this is what's represented by the T wave. So remember, we talked about how in repolarization it's the opposite way round. Positive charge will move from cells that have not yet repolarized to the ones that are repolarizing. And moreover, it starts with the subepicardial myocardium. The subepicardial myocardium, even though that was the last bit to depolarize, it repolarizes first because its action potential, its plateau phase, is shortest. Okay, so the subepicardial myocardium, that repolarizes first, and the wave of repolarization spreads in towards the subendocardial myocardium, and therefore overall the movement of current, positive charge, is outwards towards the subepicardial myocardium. Okay, and hence again we're going to get a upward deflection in our ECG trace here, because the electrical potential is going to be rising down at the left leg and lowering down at up at the right arm rather. Okay, and therefore we will get a positive electrical potential difference between the two, so this will deflect up now. And then of course, as quickly as it was produced, it will then be destroyed by extracellular currents reversing it. So we'll come back down, and then that's the end of the cardiac cycle, so we're then back to electrical neutrality between the two. We're back to the isoelectric line here. Okay, so there is my explanation then for why the ECG trace actually looks the way it does. As I say, this is just one ECG trace. We have just connected an electrode to the right arm and to the left leg and asked what is the electrical potential difference between those 2 points. That's all you do with an ECG. You're just measuring the electrical potential difference between 2 points on the surface of the body, and the reason that you actually get a fluctuating electrical potential difference between the two is because of these currents that are moving around in the heart. Okay, and those are triggering alterations in the electrical potential all over the body, and you can see this by looking at the electrical potential difference between 2 points and looking at how that will vary over a cardiac cycle. So this thing will just repeat again and again and again and again every 0.8 seconds for as long as you keep the electrodes connected there and you actually watch it. Okay, now as I say, I haven't given you any values for how big are deflections, how big these electrical potential differences actually are, and I'm not going to do that. I'm just going to talk you through the basic pattern, and I can give you the times. The reason I can't give you the exact values for how much the electrical potential difference varies is, as I've previously said, because it really does vary where you exactly put the electrodes, how big the person you're dealing with is, things like that. So the pattern remains the same and the time intervals are roughly correct, but I can't tell you how big the actual deflections will be. Right, so there's the basic explanation of why you get this famous pattern in terms of the way that the electrical signal is conducting through the heart. What we will do in the next video is we will talk about 12-lead ECG, because unfortunately the way that this is done in the clinical setting is far more complicated than this. This is just one ECG, this is one of the leads in a 12-lead ECG. In particular, this is what we will call lead 2 of an ECG. Okay, there are 11 other leads where you attach the electrodes on the body to slightly different places and you watch this whole thing from a different angle, and that can result in different but very much so related patterns. All of the patterns of ECGs are very much so related, they all have these same waves, but some of them can be upside down. For instance, you see, if I'd, instead of asking what the electrical potential difference from the right atrium to the left leg was, if I'd said, let's do it the opposite direction, let's say I want the electrical potential difference from the left leg to the right arm, I would have got this entire thing inverted, and some of the other ones are effectively just that. So if you're looking at an ECG where it's inverted, it might just be that you are looking at one where the electrodes are in the opposite order to what we've got here. Okay, and indeed, one of them that we will see is just that. Some of the others, the electrodes are in completely different positions and they give different, but as I say, very much so related pictures. Okay, so we'll come on to that in the next video.